functions of a Consteel 19. I think we can start now the presentations. My name is József Szalai. I'm the leader of the Consteel Solutions Limited company, the developer of Consteel software. And after a short introduction, my two colleagues, Dr. Bálint Vasilyevich-Sömjén and Adam Kish, will present the new functionalities in our new version. First of all, let me say some overall word about Consteel, what we think Consteel, why it is different compared to other software, and what does it mean, our slogan, truly calculate your structure. Structural design software is all about efficiency, making the whole design process more efficient. And this efficiency can have a lot of different components, since this structural engineering, this design process is part of the whole design process. That's why data transfer, import, export of the model is very important. We should collaborate with a lot of other software, a lot of other models. We can have a lot of automation in our design process, parametrization. Now we have lots of tools, scripting. We can work out design protocols to make the design faster. And there are a lot of other components of efficiency. But what we think we do primary in Consteel for this is we rely on building a real model, a realistic model, as close as possible. Based on that model, we try to evaluate the true behavior of the global structure model, and these two components are the base for the Consteel efficiency. And in the heart of that process, we have a specific finite element, beam finite element, this 7-degree freedom finite element, which we use since more than 25 years now. So we built everything around this element from the very beginning, including in the modeling phase a lot of special objects, which makes it possible to do exact positions for each objects, each members, each loads with their eccentricities and connectivities. So we have a lot of special modeling objects to do a realistic model. And based on these models, using the 7-degree of freedom finite element, we have special analysis features to obtain the true behavior of the structural model, including linear buckling analysis, imperfection analysis, sensitivity analysis. And of course, since we have the 7-degree of freedom, even the first order analysis can give different results compared to other software. This is the core of our analysis. And based on these results, we have special design solutions, making the whole design process more efficient. We are building on primary on the general method, but we have overall imperfection method. We base everything on complex calculation of thin wall cross section based on the complex stresses. And we should say that we see that 7-degree of freedom beam element is more and more popular in other software as well. And we're happy to see this because we think that we are pioneers in that process. We started it as the first software in the design structural design software community. But we should say that during this 25 years, we worked out a lot of environment to make this finite element a real practical tool in the design, increasing the efficiency of the structural engineering process. So this is what we think is the most important about Consteel, and this is what makes Consteel different compared to other software. Of course, this lot of novelties needs a special knowledge on what we are doing in Consteel. That's why last year we started the trainings about Consteel processes. And this year, these trainings were so popular. We have a lot of people participated in these trainings, and not only our users, but interested colleagues as well. So we continue this process this year, and we are inviting all of you to participate in these trainings. We have two periods for this training, the spring and the autumn period, for a couple of trainings. And if you visit our website now, the spring trainings are open for registration. So we do this training in order to deepen your knowledge in our specific solutions. And also I would like to get your attention for the our yearly award, Steel Lion Award. We have expanded categories now for this year. So we have the Steel Lion Award, we have the Pangolin Award. We introduced the cold form structure award for those models including cold form elements. It is more and more often that Consteel is used in this industry because we have a couple of advantages using this specific element and specific methods what we implemented in Consteel. In this area, cold form structure area, it is especially efficient to use Consteel. We introduced a new category for smaller projects, small scale projects. Be submitted. Want you having just smaller but interesting projects to submit into this award competition. And we will have a specific FALCON award as well for those models, including FALCON calculations for wind. And we have the student award. And now about the functions, just a summary of what are the new functions in Consteel. We have basically two development focuses in last year. The first one is FALCON. FALCON, we released the final version in the middle of last year after a half year of testing and beta period. We have a couple of improvements and developments in this period, and now we have a final version with our first plugin implemented into Consteel. Adam will talk about this. And all the others are somehow ordered around the modeling phase, which is very important also in Consteel to make more and more a possibility for you to be able to create a realistic model. We have a couple of novelties around load definitions, actions, fire actions. We have a couple of new parametric structure models, structure macros, new descript commands, new functionalities in member definitions, especially for member eccentricities, for connection handling. We have brand new functions for building efficiently tapered build-up members quite flexibly. And we have a new model error detecting and repairing tool. So these will be the package of the new functionalities. And now I give the word to Adam, who will start the presentation with FALCON.
So good morning. Thank you for coming for this webinar where I will speak more in detail about our new functionality, a new plugin called FALCON, which is our fluid dynamic aided load generator. in our Consteel environment. And let me just briefly introduce what are we talking about today. So this presentation will be a bit more pragmatic than usual. So I will, after a few introductory thoughts, I will discuss about the background and the validation procedure of this plugin, and then I will jump right into the detail and show I consider a really interesting demo where we will start from a small, actual simple box to try to capture the reality and to demonstrate the true power of FALCON. A few introductory thoughts about FALCON. I really believe that this first slide encapsulates everything about FALCON, which mainly highlights its place in our ecosystem. So as you know, Consteel is already been a software which has had tools and has tools to create meteorological loads, to generate actually meteorological loads based on the standard practice of the engineers, where obviously we have a set of standard-based parameters, velocity pressure, internal pressure, other geometric parameters, and we usually have to deal with the load evaluation procedure, which is not that simple always. So the key point of FALCON is that it is a universal load generation tool supported by fluid dynamics. So in the background, there is a CFD engine, and it operates as a standalone solution, so separated to Consteel. It is a plugin, and it is capable to integrate seamlessly in the whole load evaluation procedure. Okay, so a few thoughts about our goals. So we really, from the beginning, we really wanted to create an easy-to-use tool, because we realized that there is a tendency, similarly to the 2D and 3D, let's say, trends or beam trends. CFD is also a new, let's say, technological revolutionary procedure or approach, which is step by step is introduced, or it is used in the engineering domain and also in the AIEC industry, which obviously has a really deep knowledge, a separate subject, the subject of fluid dynamics behind it, while engineers still have their own knowledge, their own set of standard-based knowledge, mainly about wind load evaluation. So we really liked, or we had the idea to create a tool where we did our part regarding the technological research and the development to offer a tool which is easy to install, easy to license, and easy to use. Then obviously we wanted to create an easy to understand tool, where last year we launched a community testing period. So it was more than a half a year period with multiple workshop occasions, and at the really end of this period, we launched the version, or the actual full version of FALCON, or commercial version of FALCON. And through this period, obviously, we get a lot of useful model examples. How would engineers use this? And we tried to understand. Therefore, the tool became pretty easy to understand with a relatively simplified user interface. And I really believe that the most important aspect is to have an easy to adapt tool, where we obviously did our engineering research part and validations. And through further theoretical explanations, through trainings and knowledge-based materials, we really wanted to create a tool which has the background to be adaptable with the standards, to offer a tool for the engineers to compare the standard-based results where we have, obviously, and where we don't have, to have a tool which creates confidence in during its use. Okay, so really briefly about the development history. So CFD is not a new tool. It is from the early 2000s. And we actually, as our other, let's say, software developers in our domain, we are using the same engine, OpenFOAM, which is a C++ toolbox, which we, during in the past few years, we introduced as a separate plugin again in Consteel. About the background and the validation, just a few thoughts. So I really believe that today, as I said, it will be a bit more pragmatic and we don't have the chance to enter too much into the details. But I really believe that we offered a lot of tools and materials in our websites, in knowledge-based materials about, let's say, from multiple approaches, because if I would have to, let's say, summarize what's the real deal and what's the real, let's say, complexity of validating and using this kind of tool, is that we have this triangle of, let's say, approaches, where we have CFD simulation itself, which is obviously a solution, a digital wind tunnel based on a specific fluid dynamic calculation. And then obviously we have the reality, let's say, the standard practice, and the wind tunnel tests on the other hand. And unfortunately, these three, if we would like to compare on the same exact model, which we did, we actually did for multiple scenarios. We did a parametric study for hundreds of simplified geometries. We realized that obviously there is no full harmony or accordance between these three. Therefore, if we would like to use it confidently, we have to have a proper partial factor, a proper, let's say, background validation, which we implemented. About these, we spoke actually last year during our fundamentals of wind load simulation training, which will be held again in April this year, and later in autumn we will have similar, and we are planning to have even more trainings where we are dealing with the general topic of meteorological load definition and also with FALCON. So really briefly, just the results of the validation. What we did again, we compared three scenarios where we had the wind tunnel tests, we had what FALCON can produce, CFD can produce, and we have the standard, which is again a specific zoned based definition of the loads, where we, as you know, we have separate type of loads or zones on separate surfaces of our structures, on the walls, A, B, C zone, and so on. And what we did is that we tried to compare these two in order to implement FALCON, and the implementation itself is multiple dialects, which I will show you immediately. But the main idea here that I have to highlight is that there is a first step, which is the simulation itself, and the second step is based on these simulation results. We have to generate loads, and we have to be able to create usable loads for structural analysis. Okay, so what will be our today's demo example? So I prepared with a, let's say, decision-driven engineering walkthrough with FALCON, which again, I believe that shows the real power of FALCON. As Josef mentioned previously and many times, that we are keen on building realistic models. Let's have now an imaginary, bit playful, but still pretty realistic discussion with an architect who comes up with a structural design idea, a request to us to design a simple box. He starts, nothing special, simple box. And then maybe he adds later that, okay, it's actually not a simple box, even if we think at the first glance that, okay, if it is a box I can handle, I have the specific Eurocode-based loads, and even with Consteel, I can generate these really easily, and I can go on. And then he adds that, okay, the structure is actually a monopitched structure, and we still think that, okay, we can handle it because the Eurocode have something to offer for us. And then the complication is that he adds that actually it is a slanted roof. It is monopitch, but in both directions. And this obviously it's out of the context of the standards already, and we maybe can try to force certain standard-based lower evaluation processes, but we are already starting to deal with something that it is out of the standards-based procedures. And just for comparison, we realized that, okay, this, if I consider this as a closed box for a monopile structure and I run a simulation, which I can do really simply, I can get a certain result, 90 millimeters of deflection in the upward direction, which is again probably not the reality, because the architect adds that, okay, it's actually a canopy, as you can see the structure over here, where we have a spatial truss system, and it is, let's say, an entrance hall of a building, and we really have to have this open style structure with maybe rectangular columns, and on top of them this roof. And with FALCON, obviously, we can simulate results also for these kind of structures, but the real issue is that if we add maybe columns, which are again with a certain width or a certain pretty big dimensions, it will affect obviously the structure's deflection, and we have to take into consideration how much wind load will arise on these specific columns, which we can do also with FALCON. And then we realized that actually, and here I will introduce during the demo, that the reality is, let's say, more extended usually, because we above the structure and near the structure we have some kind of bounding, let's say, some kind of trapezoid or sheeting, some kind of envelope of the building, which we have to take into consideration. And ultimately, the architect actually does another, let's say, or gives another information that there will be another annex building, which again influences the results. And actually, there are surroundings around this building. There is a neighboring building, which again pretty influences the results. But fortunately, with FALCON, even for those complex scenarios where you can see that the whole building, the surrounding building, and everything were taken into consideration, we can run relatively easily, in this case, in 20 minutes, which I really believe it's a good amount of, or a relatively acceptable amount of time to wait for simulation results. We can obtain actual loads that I will show immediately, where we are realizing that actually this suction of our roof is getting even more. Okay, so let's head to Consteel, and let me briefly show how FALCON deals with this, let's say, imaginary scenario. So first of all, we are starting from this simple box, but as I said, we actually have a more tilted geometry. And if it would be some kind of monopitched, as you can see, for a monopitched structure, Consteel can use the typical or the standard-based procedure to define wind surfaces. But in these scenarios where we have out of the standard-based scenario, we should we have to use FALCON, and we can create meteorological or simulational surfaces on our building. Okay, and to define how the wind will flow, what is the effect of our wind, we have to use the same procedures that are available in Consteel regarding the velocity pressure or the wind profile definition. So the procedure is, again, it is pretty standard based according to the Eurocode. We define the terrain category, a basic wind velocity, and pretty much that's it. Then we can include internal pressure, which even in FALCON can be taken into consideration, which means nothing more than a additional load case where we are adding or subtracting a certain value to have the effect of inner, let's say, internal pressure. In this case, I'm not going to take into consideration. The geometric parameters, however, are another relevant aspect. Obviously, here we can define what is the zero direction, the positive x direction, and we have to be able to define a bounding box of our building, which we are focusing on. In this case, it is a 20 by 20 structure, as I mentioned previously. It was shown on the pictures, and with a certain ground level, which is at the zero this time. Okay, so this was the, let's say, the most basic information that we have to be able to define regarding the metrological effect. And then we have to place the simulation surface, which is just a simple selection of the surfaces. But it is really important that if I would like to consider something into my model, I have to assign this metrology or this simulation surface. And even if I have a structure beyond or in my model, the columns and obviously other steel elements won't be considered in the simulation, because everything for FALCON has to be modeled as load transfer surfaces. Why? It is really important to understand that the CFD simulations, and usually any simulation, is a finite volume based simulation using this finite volume mesh, which is again requires some solids, some volumetric geometries. Therefore, we have to model everything around our building which we want to consider. But for this simplest scenario, as I said, right now we have this closed building. Okay, pretty much everything is defined. We can go on with FALCON. As I mentioned previously, it has its main dialog where you first have to make sure that you define these effects and surfaces. You can define any type of wind direction. And then the most important aspect is to define certain simulation settings, from which two specific parameters are the most relevant. The mesh size on the structure is the actual dimension of the loads that will be projected from the simulation results to our geometry. And the mesh refinement factor is another additional meshing factor, which influences the global mesh number of our finite domain. But I will immediately explain a bit more detail on something already performed. And after that, we have certain advanced settings, which usually the default values are suitable for general use cases. The most important one is the turbulence model, which there are multiple ones, but the validation and what we considered the most suitable turbulence model was the K omega SST. So the whole validation procedure was performed with this model. We can define the domain dimension parameters. We can use multiple processors if we would like to, but obviously we can have 8, maybe 16 processors, which will create a parallel run of the simulation, which is unfortunately not always, let's say, the fastest way. So maybe the procedure of having parallel simulate or parallel runs and then combining each other can take more time. So by default, it is 1. Okay, number of iterations, convergence criteria, and another aspect, which is by default, it is not visible, but if you would like to, you can show the results of the wind tunnel or the actual mesh in which the simulation was performed. If you would like to know more about these, you can anytime click to the information button where you can get some information, a few words, but more in detail, you can find information in our documentation center. Okay, so when everything is defined and we accept the values recommended by the software, because we always try to, based on the geometry, and this is why it is important at the really beginning to define those geometric parameters, we are trying to define a certain mesh size on the structure, which is suitable for that specific scenario. In this case, 2 meters, and we leave the refinement factors with 2, and let's run our first simulation only in one direction. And it always saves the model, and for this simple scenario, as you can see, it is relatively fast. The meshing procedure is just finished in 10 seconds, and then the actual simulation is performing. And immediately, when it reaches convergence at 30%, we'll finish, and a specific load case and the geometry of the wind tunnel will be sent to Consteel. Additional information during the simulation can be read. If there are some warnings, errors regarding the geometry here, you can check it. Okay, so this was the wind simulation part. The next procedure would be to go to the wind load generation, and I can go directly from here, or we have a separate dialog for that. But first, let me just quickly show. I forgot to enable the wind tunnel. I will show then on another example. Let's then generate the actual loads. If we have a certain direction, in this case, we have the wind direction 0 only available. We don't have internal pressure defined, so we cannot run. But what we have to define is the load generation, let's say, procedure or method, which relates to the zoning method, how we consider, how we are, let's say, simplifying the results of the simulation. There are 3 options. If I consider that I don't want any type of zoning, which means that I would actually like to apply the direct results of the simulation, this is what will happen. So it immediately creates some loads on my load case, in this wind simulation 0. And as you can see, these are the actual results which were projected to our geometry based on a simulation. If you are using FALCON, I really, let's say, would like to recommend a few things. First, use the layers just to make sure that you can easily create the geometry or the model or the surface model of the building, the envelope, and separate the actual structure, the actual wireframe of your structure that you will design. So I really believe it is important to use layers, and obviously to use certain visibility scenarios about what you would, or for what you would like to see certain steps. For example, you can just simply hide everything just to make it more understandable, the actual load around the building. So this was our first result without zoning, and let's just check it, what happens with the other scenarios. So global would mean that it is already has certain load evaluation setups, or you can have a few parameters regarding how many zones globally you would like to see on your actual scenario, without any multiplication factor or any other factors by default. And let's run it, what happens. And remember, we let these 8 specific zones to be created, and this is what we see ultimately, that we have multiple already zones, already combined faces of the result mesh, which makes more easy to run, because right now we have just only 18 loads, and previously I forgot to actually select all, but we had hundreds of specific loads. And what happens during categorized scenario, is that we try to implement a solution which really tries to follow the procedure or the general approach of the Eurocode, where everything starts with defining certain surface types. Because in the Eurocode, you know that we have to first define the windward wall and the leeward wall, and similarly sidewalls, roof, and then we have separate values and other maybe zones, A, B, C zones for the sidewalls. And FALCON automatically can categorize these type of surfaces in these four surface types in order to assign specific parameters for the load generation. So, for example, and we can anytime check it which are considered as sidewalls. And as you can see, these two will be, obviously it is really easy right now, based on the actual wind direction, obviously, because from the zero, these are the sidewalls. And let's just check what type of parameters are set by default. So as I mentioned previously, based on the validation results, we have a certain multiplication factor, which we considered that is an additional percentage, additional partial or safety factor in order to be able to create something more close to the Eurocode for the simple setups, which ultimately, when we would like to extrapolate for more complex cases, can be or can offer more confidence. And then number of the zones, again, I can define that I want, for example, sidewalls usually 3 zones to see, but obviously there is a zone interval limit. So maybe if my wall is too short and the results are too close, or the intensity of the loads are too close to each other, there will be no actually 3 zones. There can be a merging of these zones based on the difference of the intensity, and this is the zone interval limit. And there is a mesh size factor, which I will show immediately on another example what it does. It just offers the possibility to ultimately, let's say, even if we had a precise, and we would like to have a precise calculation, the load definition process to be more conservative on bigger, let's say, loads. But I will explain immediately. And the last thing that we can influence is the external pressure limits. So at the really end of the load evaluation process, we will get surface loads, which have a certain velocity pressure based on the reference height and a certain external pressure CPA according to the Eurocode, which is again pretty, let's say, familiar to the Eurocode terminology. And if we would like to be a bit more conservative, but still to make sure that we have at least minus 0.5 suction maybe for our walls, to have a C zone which is all along our specific wall, we can have this type of limit, because the tendency of the wind flow maybe, or the distribution of the suction, can go really to zero, and maybe just to stop at a certain limit, we can have these kind of setups. Okay, so pretty much these are the generation possibilities. And I really believe that FALCON usually, and we don't have the chance, maybe during the trainings, this is what we did usually, that it is an iterative process. And obviously this is time consuming to see multiple, let's say, generation results, while how they can maybe influence the actual deformation of the structure, because we maybe run analysis using these load cases. But anyway, the idea is that iteratively we have to be able to understand what the specific simulation case does with our structure. Okay, so let's run the categorized solution, which is again offers in this case a pretty similar result to the wind Yeah, I did that. Okay, so pretty similar to the global, but the idea is that we have multiple zones. And if you select a specific load, as I mentioned previously, these are actual surface wind loads with a certain velocity pressure at the reference height, which is the top of the building or the top of the surface, and the specific external pressure coefficients, which is minus 1.2, pretty close to the A zone of the Eurocode. Anyway, this was obviously the most simplest scenario. Let me show a bit more complex case and explain a bit more detail the simulation procedure itself. So as I mentioned previously, we can also suppose that this structure is a simple canopy. So here would be the results. The simulation procedure would be similar, but maybe the mesh sizes or the default values, as you can see from the previous 2 meters, it is in this case just 1 meter, because we have a thinner, let's say, envelope, and just to make sure that we have enough mesh faces on our surfaces, the software automatically recommends a lower value. But we can run separately for this scenario, which I did previously. And as you can see, this would be the actual domain around the yeah, and I will also show this one around our building. So what you can see here is, I will hide actually everything else, just see first the red, which was the previous scenario where we had the full closed building taken into consideration. And as you can see, a negative of the structure, let's say, was created in order to have a finite dolom, which obviously has a certain height and everything, but we only show the ground, because by this you can feel the actual extent and the actual dimensions of the meshes. And what I would like to explain here is that if you remember, previously we had a mesh size on structure of 2 meters, which is obviously an approximate value, but this is what we have. So near the building and on the building, we have 2 meters. And what does that specific refinement factor does is that, because obviously we would have a more precise result only around the building, and maybe far away from the building is enough to have let's say a lower number or smaller number of mesh cells during the simulation, which obviously means faster simulation, we can decrease or actually increase the size of the meshes. And by choosing the default 2 value of the refinement factor, what happens that first we have a 4 meter and ultimately we have a 8 meter mesh size close to the inlet of the finite domain, which means that we actually doubled 2 times our initial value. This is what happens. So 2 meters doubled 2 times, 2 on the power of 2 ends up with 8 meters. Obviously, you have to be careful because this 8 meter cell or mesh size influences the wind profile, the inlet wind profile, which again, what is the goal is that ultimately to offer an inlet profile as close to the Eurocode as possible. And in this case, with terrain category 4, we have a minimum value or a constant value below 10 meters. So we should have at least 10 meter mesh size. In this case, we have 8 meters, so it's okay. So we have at 8 meter mesh size, then at 16 meter, and we will have actually a bit, let's say, linear profile, but still close. If my mesh size is maybe higher and I'm ending up with maybe a 32 meter of inlet size, you can imagine that the actual wind profile of the Eurocode will be lost. So this is why or how we are trying to recommend those, let's say, initial values during the simulation. because these can lead to more proper results, even if they maybe can take a bit more time. Okay, so this was our previous setup, and let's see the setup with only with the canopy. And as you can see that it is pretty similar, but because the 1 meter mesh size, we have 2 mesh faces actually on the canopy, but pretty much the rest of it is similarly, because from 1 meter we had a refinement factor of 3 and we end up with the same result. Okay, so pretty much this is the procedure of how you can understand actually what happens during the simulation, which is obviously not mandatory always, but at the really beginning maybe of the projects, or when you start the load evaluation process and you want to make sure that the simulation or your simulation performs as it has to, it is recommended. And then what I did, I will show a few another scenarios, just really briefly, what I've shown during my slides, that I considered the building when I have hide the loads. When yes, we started with the canopy, just to, and then for the closed scenario, the canopy and the canopy with the columns. And in this case, you can see that I use the actual geometry of the columns, and probably because we are creating our wireframe models, these are actually not reflecting the reality, because our canopy has a certain extended geometry, because obviously our surface maybe ends at the edges of the columns, and maybe we have actually a higher building because we have a certain envelope, certain again maybe a purlin system, a trapezoidal sheeting, anything else, and actually we have a higher canopy, or a bigger extended version of our surfaces, which would arise maybe questions. Okay, I can design it, but then how I will project these surface results to my actual wireframe model. And this is where I would like to also introduce during this demo our newest feature regarding the load transfer surfaces, or the extended version of these, which means actually a simple, let's say, additional approach. During load distribution, you can consider with Consteel 19 a certain limit value. So if your surface is so it is below, the distance between your structure and your surface is below 1 meter, you can project the results, even if they are not in the same plane, to your wireframe model. And let's see it. So in this scenario, we have certain wind surface loads, both on the canopy and on the column. And if you can, as you can see immediately, if I showing the wireframe of the building, we can distribute directly to the elements, even if they are not in the same plane. Because if you select a certain load transfer surface, you can check which are the selected members. Obviously, in this case, we cannot use the planar members because they are not in the actual plane. But if you go to the planar members and then back to the selected, you can see that these are with the yellow, which are with the below this certain limitation. Okay, and actually, this is how it is possible to go from this to a distributed load scenario, which ultimately will be considered during the finite element mesh creation. And actually, this is always the actual distributed version of your load. So I recommend to follow these steps and make sure that your actual surface load will be distributed to your wireframe model. Okay, so this, let me show you a bit more complicated scenario, as I promised, that maybe let's suppose that actually we have a additional whole building, which obviously are influencing the results. Why? Because there will be a certain vertices will be creating, and because that there will be a certain pressure close to this, it affects also the roof at a certain level, and the actual uplifting of the roof structure will be a bit higher. This is why when we actually are using these results of our simulation result, the actual load case for calculation, you can see that the results are even higher than with the previous case, where I think I actually forget to show. Maybe let's see that canopy scenario. Yeah, this one, where we had maximum of only 10 millimeters. And you can imagine that obviously it can really affect our structure. And these are approaches that we cannot take into, or aspects that we cannot take into consideration just by simulation. Okay, so obviously, as I said, the reality is usually even more complicated, because we can have even maybe surrounding buildings. And as you can see, I just run a scenario where is actually it is from 45 degree of 45, meaning that it is from this direction the wind will flow, and I obtain these kind of results. And actually I can show you also the version with 0. So from this direction, and what it is important that, or what you can see, that even if you don't have loads on this neighboring structure, why? Because these were defined as obstacles during the mesh surface or the simulation surface definition. These are actually the only parameter that you can decide. If you choose to be general, it means that there will be loads created. If you choose that there are obstacles, there will be no loads generated. So pretty much that's the result of this scenario, where close to the building will be a bit higher suctional values due to the channeling effect, and even at the side of your annex building will be a slight difference in the results. And the last thing that I wanted to show, that maybe these kind of results are still you have too much meshes, and maybe you would like to have a bit more conservative approach. And I don't have the results. Maybe then I will show this scenario. So anytime you can choose to create a mesh which has a certain mesh size factor a bit higher, which you will see immediately what it does. As you can see, this mesh is let's say too precise. We have too complex polygon of the loads. Maybe we would like to see some more bit more simplified mesh, which looks something like this. So remember, we always have to take care to run result or simulations which are let's say, precise enough, because in the background of this simulation, what we had is a relatively precise mesh size. As you can see, even this building or neighboring building was taken into consideration in the finite domain, even if there are no loads on it. So we have to have a precise model enough, and ultimately we can create more, let's say, conservative loads, which are as close to the reality as possible still. Okay, so this was my brief introduction of how I see what is the real power of FALCON. And again, I would like to invite to our trainings and check our knowledge base materials, which we are trying to constantly upload more materials, and see you soon. Thank you. And I will give the word to my colleague, Vasiljevich Balint. So thank you for the attention.
Good morning, dear colleagues. My name is Balint Vasiljevich. I will be the presenter of the last part of today's webinar to speak about other new features implemented in Consteel 19. First of all, this is again just an introduction. We definitely say that Consteel is a software for steel structures, but it's a general software for steel structures. So it's not fine-tuned for any type of segment inside of steel structures. There are many people who are using it for industrial halls. There are others who are using it for photovoltaic elements, others who are using it for multi-story buildings, sometimes even theaters, sports stadium roofs. A lot of things are used. But somehow, if we see the projects of customers, also which are sent to the steel line competition, or also those which appear during our support activity with any sort of question related. Plus, if you see the interest of the newcomers, those people who are downloading trial version, and they specify what is the type of problem they're looking for a software, then there is a surprisingly big number of people who mention steel halls. And also when we do trainings and presentations, then we usually realize that for most of the Consteel functionalities, really the halls are the most interesting projects to demonstrate the strengths of Consteel. This is because steel halls are those structures where usually there is relatively big span requirement, sometimes even height requirement. These structures are not architecturally demanding beautiful projects in most of the times, which means that the cost of the construction is very strongly connected to the cost or price of the steel structure. If there is a strong competition and the contractor who finally wins the project needs to offer a structure which is as light as possible. Big span, big heights, slender structures, and need of optimization. Obviously, here stability becomes always an important question. Due to the small sections and the big spans, plus the not so obvious lateral stabilization system. Imagine if you have a multi-story building, it's relatively easy. You have everywhere columns, which are anyway carrying huge axial loads. The structure, the building itself is usually stabilized by shear concrete, shear walls around the elevators or staircases. So basically the steel columns, they are just pin structures or more or less close to a pin configuration, and they mostly carry vertical load. Their buckling length is equal to the floor height, which is something like 3-4 meters. If you have a decent size of hair profile, buckling doesn't play any interesting and any important role to be checked. The floor beams are all supporting the concrete floor. Top flange is continuously stabilized laterally by the concrete or by the trapezoid. The deck what is connected to. Therefore, there is really no very high need to make stability verification. On the other hand, if you see any of those examples which I have on the screen, then you will see structures here which are really light, made of slender elements, and very often they are stabilized by not very strong secondary elements. It might be a decision of the engineer to utilize these secondary elements of stabilization or not, or even more exotically use the sheeting, trapezoidal deck, sandwich panels, or others as stabilization or not. It's always a continuous debate whether this is a good idea to utilize these elements or not. I don't want to be the judge. We are just willing to offer a software which can do this task. So finally, it becomes always evident that although Consteel is not for holes only, but it's very important for the success of Consteel and really to show its capabilities for buckling verification, that it becomes more and more applicable for the special demands of steel structures made for hole structures. Hole structures are very often made by non-conventional solutions. This might include profiles, members with non-uniform cross-sections, cold form sections, eccentricity always is present on these structures, and the whole together becomes a really demanding and interesting problem to be solved. And we are 100% convinced that Consteel is able to solve this, and that's why we are also, as a sort of strategy for the future, we definitely would want to focus even more visibly on hole structures. It doesn't mean that we will not focus on other steel structures as well. Of course, Consteel will always be a steel structure design software, but now, from now on, there will be an even more expressed concentration on the holes, because we want to reach that goal, what we made for ourselves, that we want Consteel to become the best software at the moment in Europe, based on Eurocode, hopefully later also worldwide. We are working on an AISC version of Consteel, which is the American standard, if some of you doesn't know, AISC 60. Our goal is, first step, to be the best software producers for holes, steel holes in Europe, and second, worldwide. In order to support a bit this sort of activity and your activity to make more holes, much more easily definition, plus to showcase also the capabilities of the scripting environment within Consteel, we created 6 new scripts. These are basically 3 times the same. One option is 2D intermediate frame. The other corresponding option is the 3D building of having the same intermediate frame as in the separate 2D model. The geometry of these buildings is very simply. Of course, there are many parameters which can be used to change the dimensions, heights, and everything, number of frames, distances, and such. And all 3 are basically the same buildings. What is different is the structural solution, primary structural solution, what is used for the load-bearing structure. One is following the most traditional approach when hot rod beams, columns are used, and near the column connection, hunches are used for the region with the higher bending moment demand. The other option uses welded section, and the third is probably most interesting, uses cold form sections back to each other. These macros can be found in the parametric model library of Consteel, but as always, you may feel that these are not complete enough for you. These are always free to extend. You may need to have a certain membership to have access to the source code of the scripts that we are developing, to have a chance to modify them freely according to your wish. But anyway, you can always start to make something for yourself. So this is also just giving ideas how many different things are possible to do in the script, which can make the life easier to model and also to calculate structures. One of the new, very interesting functionality of Consteel is a new member eccentricity type. In Consteel, if you remember, those who are long-time Consteel users, there was always the possibility for several components to define the eccentric location, not simply just by entering an offset value in millimeters in the different directions of the plane, but it was always possible to use some special nodes, special points around the bounding box of the profile. These were typically those which are visible on the screen, around the perimeter plus the reference line, the middle position of the bounding box. This sort of functionality existed in Consteel since ever for the point supports, for the loads, point loads, also linearly distributed loads, also for the smart links when we define the end or the starting position of the smart link, and it was also available for the placement of the of the shear field objects, which are to simulate the shear stiffness of roof systems. And now what we did now is that we introduced the same possibility for the elements, for the line elements, columns, and beams in Consteel. And we haven't just simply introduced this possibility for the element, for these elements, but at the same time we also extended the number of applicable points which can be used as special points of the profile. So as you can see on the picture on the right side, these are not only the points along the perimeter and the center position of the bounding box, but now also as also the picture suggests, in case of a monosymmetric section, of course we may have different, not necessarily the shear center is at the same position of the bounding box middle point, and also what we added now, trying to focusing on a much more useful work for welded elements, is that now new points have been added at the intersection of the web to the flanges and also a middle web position. Very often these are very practical and useful reference points when somebody works with welded sections forming an I section from 3 plates. I'll be just showing just very small examples how it can be used. This is a bit similar to what always existed, for example, in Tekla and many other softwares, that you can select elements and you can model them with eccentricity. There is always something important to remember, that it might be tricky to work always with eccentricity. Actually, eccentricity is always existed in Consteel. What is now different is that you don't need to calculate each time the different millimeter values to find out the correct shift, but Consteel can do it for you automatically. Let's see, for example, this example. Here we have primary beams, secondary beams, and at certain position also some sort of additional beams to box, to frame an opening in the floor. As the simplest way of modeling, now everything was modeled in the same plane, like it is done anyway in many softwares which are not able to work with eccentricities. In Consteel, we always say that it's very important to work with eccentricities. Therefore, we don't never recommend to keep a model like this, because if the model is kept like that, then all those parameters what we try to obtain from the model, mainly for the buckling verification and second-order analysis, they might be not necessarily as accurate as they should be. So what is important to really set the eccentricities. Up to now, as I said, eccentricity always existed in Consteel, but in order to start from such a modeling when everything was modeled at the same plane, the engineer had to calculate the correct shift value and according to the actual size of the profile and shift them accordingly. If the sections are double symmetric, it's relatively easy because then the center of gravity, which is originally used for modeling, is in the middle of the height, so therefore just the half of the section height must be calculated with. But if these are monosymmetric sections, then it's also more complicated to find out where is the center of gravity. Plus, when we rotate the profiles, then obviously there we need to have again a new position. So in Consteel now, it is possible to use the eccentricities immediately when an element is defined. Immediately can be defined with a right eccentricity. And also later on, like always typical in Consteel, if I select an element, then we can see all the properties on the right side, and we can also change them like that. So what I can do, for example, now is that I want to move all the beams to have the top of steel at the same plane to easily accept the trapezoid deck or concrete panels or everything which we place above. And I don't want to calculate, of course, the eccentricities. I would like to do it something simply. What is visible now is that the main beam is now placed, like also the others, it's placed with the center of gravity. That means that from the zero level, half of the section height is above and another half is below. I would like to keep in my model this same positioning. What I only want is to have all the elements having the same top as my primary beam. This I can do in 2 steps with the new function. First of all, I can select all the elements all together, and simply I can just change the common position, which at the moment is reference line, to a top middle position. Once I select everything to the top middle, sorry, I was almost good. There was a shift in the model, which I need to delete first. Okay, so I selected all the elements to have, instead of the reference line as a new reference, the top middle. And what you can see is that now automatically all elements are sharing the same top level. What didn't happen is that now also my beam has moved down. So it didn't happen what I wanted, that the main beam remains in its original position and all are adjusted to the top. What happened is that all have been moved together to fulfill the first instruction, that they top be exactly the same level as the original reference was. In order to obtain what I originally wanted, I can select all the elements in the second step and simply just move them with the original shift of 300 millimeter above. And now everything is what I wanted. The elements all have the same top level, and the main beam is located as it is. Of course, here what happened is that the reference line didn't move, but what has changed is that all the members became eccentric. I will speak about later a bit more about whether to model with eccentricities or try to model with the centric type of modeling and use smart links. This is always, again, a sort of question when it is the best. Sometimes it's easier, especially now with this offset function. It's much more easy to shift to set locations of the elements. But on the other hand, some people prefer to use still a central-line modeling, and for that we have the smart links and other link elements. In general, what I already can tell now, that in my opinion, the best is if the reference line of at least the most important elements should remain somewhere inside of the sections. Actually, mathematically doesn't really matter, but to work with all the boundary conditions, supports, hinges, and others, sometimes modeling where the reference line is strongly outside of the section gives very strange, unaccepted results and difficult to control. So it's much easier always that even if we work with eccentricities, to have the reference line as close as possible to the original center of gravity of the section. Of course, now if we have several members, it is impossible to have all with the reference line at the center of gravity. In this case, visibly, for example, here in the smallest beam, the beam is here above, and now its reference line is well outside of the profile. It's always a question. I always recommend for you to not just blindly do something, always see if the models are close to what you expect or not. In Consteel, we are doing correctly all the eccentricities on the level of stiffness matrices, so mathematically everything is correct, but of course, a lot of features you may lose if you don't have really the eccentricities of the elements. How otherwise can still be used this sort of new functionality? Of course, if you have, for example, a column carrying a crane, it's very typical that we have a deeper section below the crane and a smaller above. Again, if we just model everything with the straight line, then of course there will be no correct eccentricity. One option is that you calculate the value and you enter by hand the eccentricity value. Other option which appears now is to set a plane, like for example the top of steel, which is a straight line, and you adjust the elements to that. Here I just made referring to my previous discussion, and as an alternative model, the other possibility, when simply we use always as reference line the center of gravity of the profiles, and we connect the abrupt jump to connect the lines with a rigid element or with a link element. This is also possible. As you can see on the right side, the deformed shape is exactly the same. So for such easy simplification, when there are no any hinges, everything is continuous, of course, the results are the same. But there might be some situations when it's still much more easy to control, especially the position of releases, to really fine-tune the connection between elements when we are modeling with the center lines. So this eccentricity is a new possibility. Use it where it makes sense, but don't forget that there is also other possibility. And although on simple member levels it gives the identical results, when you start to be at more complicated structures, sometimes it might be more challenging to get the correct result with eccentricities, and some special things, especially related to positioning of releases, are simply not available when you work with eccentricities. Another possibility typically used for holes is when somebody works with hollow sections, is that for part of the rafter, a deeper section is used and then a smaller, and again, they can be very nicely adjusted to each other without doing any calculations of the eccentricities. A bit back again to the situation when it is a bit more delicate, when we are working with welded sections. And let's assume that we have a beam which is made by any reason of two segments. One has a profile like on the right side, which is nicely a double symmetric section, and by any reason for the part to the left, we wanted to extend the thickness of the upper flange by a certain additional millimeters. Of course, now if we make the modeling in Consteel with the reference lines, originally a straight line, and then we define the two profiles by ourselves, and then we place them as we usually do. Consteel will automatically by default position, unless we do anything with the eccentricities, Consteel by default we place the beams, these segments, with the center of gravity to the reference line I originally gave. In case of a monosymmetric section, as I already said at the beginning, the center of gravity is not located at the mid-height of the profile. So that means that when I place the two elements to the same line, then what I will see is that they are visibly not in the same line. So the problem is not just that they are not well adjusted by the top of the web as I wanted, but they are also visibly very misplaced, because one element is at the location where I believe it makes sense, but the other is certainly shifted below due to the shift of the center of gravity relative to the mid-height of the profile. Now, I saw many projects when people didn't care too much and they made the project like that and used for that. I wouldn't say it's completely wrong, as long as we just have a simply supported rafter and we are interested in the deflection of it or bending moment only, no axial force, nothing special, that's fine. But if we have also axial force or other other type of effects on it, then this sort of modeling, of course, starts to not represent the reality. And again, our principle number one with Consteel, that please try to use always realistic models. If you make such models which have such sort of shifts, not every result will be accurate. And of course, they cannot correct it. Consteel doesn't know that the structure in reality doesn't look like this. Consteel will just blindly follow everything what is given and will maybe do calculations with inaccurate results. So now with the new functionality, we can use also the adjusting, but instead of using now the top of profile, we can use the new position number 10, which is cross-section dependent. So obviously these sort of positions like web connection with the flange are already found on profiles which have web and flanges. But if case of an I-section, a welded I-section, it's certainly a profile which has a web and also a flange. So therefore, if we define now as an adjustment point, not the top of profile, but the top of web, then we will get exactly what is visible on the screen without doing any calculation of shifts and without doing anything more time-consuming and other exercise. Another option that I personally prefer to use is not the top of profile and not top of web, but a certain other value, top of section or top of web, plus a certain offset. Obviously, most of steel structures need bracing, and bracing is very often is made by such diagonal elements. If this is a rafter, a slope, then it follows the slope. If it's a column, then it's vertical, but the column sometimes is not vertical, so it doesn't matter. But usually we don't want the bracing not to be in a plane. The bracing is typically something which tries to remain a certain plane, even if the profile itself may have its position, especially in case of a welded section. The top of section is maybe sometimes above, higher. It's a bit fluctuating, but we don't want the bracing to be not in the same plane. So therefore, what is also possible, and this what I realized when we started to make this function development, is that I always build all my models like this, that I use as reference line, I draw as reference line the plane of the bracing, and which is very helpful because I can immediately use the nodes on the line to draw my bracing. I don't need to create any link element. I don't need to do any calculation and add manually link elements. I can simply draw the diagonal elements of the compression pipes or the rods directly, starting from the two lines I made as reference. And of course, I don't want this line to be the reference also for my element because they're not necessarily here. In every bigger engineering systems, building systems, and also if somebody makes often buildings for themselves, they may have some sort of standardized connections to make the bracing, which may justify to sooner or later create some sort of standard distances of the bracing plane relative to the top of the web or the top of the profile, as we wish. So it's already very handy if we have such standardized offsets, then we can use as reference line, reference plane, the bracing, directly model the bracing where they are, and place all the elements with the way that their top should be with a certain distance, let's say 150 millimeter in this case, with the top from the reference line. So the two information can be mixed. So not only the new positions can be used as reference, but also an offset value can be defined. And with this, there is quite a nice possibility to define any sort of positions. And what is nice, and I will show it on the last example, if you work like this, then Consteel is always remembering this structure. These are not hand-calculated value. So top of section is not a hand-given fixed value. This is a dynamic value. If I change the profile, this value will be re-evaluated and changed accordingly. So for example, if we have this sort of configuration, and if by any reason I want to change the depth of my beam to be deeper, then it will definitely move down. So the top will remain in the original position because I clearly made the top should be at 150 millimeter from the line. I changed, as long as I change nothing in the positional reference line, this is a strict rule to follow. If I change the profile, this rule, top remains at 100 millimeter from the reference line, is still valid. So that means that the profile will adapt accordingly and will move to inside of the building. So that means that if we work with the profile, we optimize the frame and we change the profiles, then we will not see that the geometry is always changing and the structure becomes wider and narrower or higher or lower. Everything, so the outer geometry will remain as it was originally fixed, and all the changes will happen to inside, which is very important if we really want to have a flexibility of playing with the different profiles. Regarding the smart link, as I said, eccentricity, now we have a more handful way to define eccentricity, but of course, it's also very important that we still remember that we have the other modeling option that we work with centric modeling of the profiles, and then the offsets are not again calculated by hand, but are made by the smart link elements. The smart links at the moment had a huge, in my opinion, quite huge range of possibilities, but it was not fully available for everything. So for example, if we had such a frame, in this case a monopitch frame with an inclined roof, and I wanted to place a column at a certain location. Of course, first idea is to use a smart link. I know where is the intersection of my column position with the reference line of my rafter. The reference line can be anything, can be even eccentric or centric position, doesn't matter. But what is important that I could easily connect my column to here. Again, if I'm just blindly making a model like often done by people without really thinking on how the structure really looks like, then as a quick option, one could simply just make a column from base to the center line to the intersection of the center line and simply create a hinge connection. But in reality, that hinge connection is probably not happening really at the level of the intersection, but it's most probably, depending of course on the detail, how the detail is made. But if we follow something very typical, that we have a bolted connection of the column, the pipe ends right below the rafter, and there is a bolted connection between the two there. In this case, let's assume a pinned connection, then actually the location of the pin is not here at the intersection of the red line with the reference line rafter, but exactly at the level of the bottom of my rafter. SmartLink is very nice, but up to now, SmartLink is always able to make the appropriate length in a direction which is perpendicular to the reference line. Here, for example, you can see all the smart links for the purlins. All these orange color link elements are all perpendicular to the black reference line, which means that they are not vertical. So if I wanted to use the same idea for my column, then actually my column would be mispositioned by a certain millimeters to the left or right. So this is not only just aesthetically nice, and of course, if I export it later to Tekla or EFC or any other mean that, of course, I may have a certain millimeters of deviation. But additionally, if this is a pinned connection, it will create an additional bending moment, which is not really happening in reality. So we want to model everything as precisely as possible. I would like this link element to be vertical. Now, there is a new possibility in Consteel. We haven't released this function yet. We had some internal issues, so therefore in the version that you have, this is not found. We will have in about 2 weeks or 3 weeks a new update release, and then it will already be there. Okay, so if you check it now, don't be surprised that you don't see it yet. So what you will see within 3 weeks is that we added a new radio button. There was no radio button up to now at all because the definition was always in the local system. Local means perpendicular to the actual inclination. Now we added the other new option, which is set global, and we set it to global, then we will be able to make a vertical line. I just show it now because you cannot try it for yourself, just to really show that it is really working. This is an unreleased version of Consteel, that's why it has. So if we go to the link elements, then now there is this new possibility with the local global. I can select global because I want to go now in a vertical direction, and I want to go to the bottom middle position of my column, of my beam. I click the intersection points, and what you can already see now, I make it a bit bigger, didn't become bigger, but here there is already a link element created. The link element is exactly behind my line, that's why I don't see it separately. But when I select it, then I will certainly see that it is certainly starting from the reference line, and it is really, and it's vertical, and it ends at the level of the bottom of my rafter. So now I'm able to position a column, and I want to make the column, let's say a pipe. On the top, I want a hinge in a bidirectional hinge. And then I start from 0 level and I go up to the end of the smart link. Now, of course, there is nothing special in it. We have here the column as it is. I can put a support. Without support, there is no calculation, of course. And now what I can also do now, and I will show a calculation because I want to show you something. So I place the hinge here. So the hinge location is here, below the element, not here above where some people would automatically, because it's much simpler to make it there, but that's a huge difference. I will show why is there a huge difference, but is might be extremely critical when somebody works with metal buildings. Sorry, I didn't select the right hinge position. Okay, like this. Okay, so one thing what is already very helpful, because I use the smart link. Of course, the smart link means that the length is not calculated and introduced by hand, but this is a dynamic thing. So for example, if now by any reason I feel that this element must be changed, and maybe I want to say that this is actually better 1000, then what you can see is that my column automatically became shorter. The hinge position was always adjusted automatically to the actual depth of my rafter. So let's say that I'm happy with this 1000. I change this is to also to 1000. Okay, this is such a heavy structure, probably makes no sense. And I just quickly want to calculate, and when I calculate, there is something that I want to see. Why was it very important to make the adjustment like this? Up to now, when you just look to the internal force diagrams, there is nothing really special here. All the bending moment diagrams, normal force diagram, everything looks the same as we wanted. So actually, if the hinge was here or there, wouldn't make any difference in this level. But if we want to make a buckling verification of the column, of course, in Consteel, everything is made with linear buckling analysis, and then we run the linear buckling analysis just by activating the buckling analysis calculation, and we observe the different buckling modes. Then what we can see now is that this column is moving as a rigid body. It's a sway-like of deformation. It's not bending, it's straight. And what happens is that it completely kills my rafter. I have here a hinged connection. This is acting not at the center of the rotation at shear center, but eccentric to that with a hinge connection. That means that this is a destabilizing effect without any stiffness to stabilize. And that immediately causes a very strong torsion to the rafter. I'm unfortunately quite sure that sometimes people forget this phenomenon, which is something very important, and you must be aware. Again, if you work a software different from Consteel, you will never see it. You make a model, and actually from this point of view, it doesn't matter that you made the hinge connection location at the right level or not. If you use a software which doesn't have this linear buckling calculation capabilities, you will never see such a direct result, especially which has an effect on torsion. So if you really want to make such a connection with a hinge connection, then you somehow need to make sure to additionally stabilize the bottom flange by flange braces or additional pipes or something, or you need to make sure that you never make a hinge connection. So you make this connection moment bearing in the out of plane direction to make sure that this sort of buckling can never happen. Back to my presentation. And now we come to the the biggest development what we had in Consteel 19, at least for structural modeling part. As I said again at the very beginning, we want to focus more, or not focus more, but support better the creation of primary structures for whole structures, which are very often made of welded elements. A welded element typically means that it's not one profile is from point A to point B, but something welded from plate is placed between point A and point B. And of course, if I weld some plates together, there is no any rule that these plates must always have the same dimensions from the start to end. I can easily make a web tapering, which means that I can linearly change the height of the web simply by using not a rectangular, but a trapezoid type of plate for the web, and also I can change the flanges along the length. So like also in one of the previous example, I changed the thickness of the upper flange due to any reason along the length. This is easy to be done in case of welded section. Of course, if you use with welded sections, with hot rod sections, then these are much more limited. The option what I can change is just use a completely different profile after a certain level. For that I have shown an example. The new eccentricity nicely solves it. There is no any other need to better support that activity, or we can add also hunches. This always existed, not always, but since almost always existed the Consteel. So I think the modeling of hot rod sections is nicely solved with the eccentricity, but if we want to speak model welded section, then there were up to now a lot of difficulties with Consteel. Imagine now the situation, which is a simply supported rafter. At the moment, it's the web is parallel, so it's not a web tapered element, but why not? I was using 3 different thicknesses for the web. So I started with a 5 mm thick web, continued by a 20. Don't look to the number, of course, they are crazy. No one would do a 50 millimeter thick web. I just wanted to make sure that the difference, the jump is visible on the screen. So I started with a 5 millimeter, continued for 2000 millimeter, then a 20 millimeter for a 1 meter, and 50 millimeter for the rest. Also for the upper flange, I used different jumps. Started for the first two 1500 millimeter, a thickness of 40 millimeter. My flange is 200 millimeter on the top. Then I continued the longer part, 3 meter long with just 24, and for the rest, only 10, and also other thing for the bottom. Now, if you wanted to model such a structure in Consteel today, and actually I think in any other software is the same, then that's the rule in every software. For a segment, you need a profile. You cannot typically change such internal parameters as the plate web thickness along the length without defining a new profile and the corresponding new segment. So at least in Consteel, and I think also in other software, this could only be done by creating 1, 2, 3, 4, 5, 6 different segments. For each segment, carefully check what is the actual thick parameter of the upper flange, the web, and the bottom flange. Define the profiles like that. Place them on the same reference line, solve the problem of eccentricities because these are strongly monosymmetric. And when I place them, of course, the same situation happens, that they will be automatically adjusted by the reference line, which is the center of gravity, which is not in the middle of the profile. So therefore, it looks very messy when I first made it. Up to now in Consteel, I had to calculate these deviation, these shift values by hand and adjust them back to the right location. And then I was happy as long as I wanted to change anything. Because if I wanted to change anything, let's say just move this change of web by 200 millimeters to the left, that means that all the affected parts need to be remade, new profiles to be defined, and new segments to be made. And even worse, if I add an additional change, which I didn't have before, because then it may affect even more segments. And again, if I do the optimization and I need to change something, then I need to do again and again. So it was a very time-consuming exercise to make the different cross-sections for each different segment, place them manually to the correct length, place manually the eccentricity to have the desired adjustment of maybe top of beam or top of web or anything I really wanted. And there is also a sort of automatic consequence that we have more and more members in my model, which is normally not a problem as long as some of you were not interested in our new product, which is called Consteel Lite. Consteel Lite is a full version of Consteel with all the limitations, or with all the functionalities included, which mean fire design, seismic design, composite beam, connections, export, import capabilities, everything is there. With the only difference is that it has a smaller price. This sort of Consteel Lite is dedicated or intended to handle smaller projects like smaller industrial halls, or a bicycle storage, or a solar panel carrying structure, or a roof structure made of steel with some glazed elements between. So basically everything smaller scale can be done with the Consteel Lite. Consteel can for the price of 50% of the actual version of Consteel, can also later on be upgraded without any problem to the full version if somebody wishes. And the limitation is related to the members it can handle. Up to now, the limitation is 250 beam elements and 50 shell elements. Very important, these are not finite elements, so the 250 are not the finite elements, but really the beam objects. Now, if we had to do the segmentation by the old style, that would have mean 6 beams to model just one. But now with the new function, new feature, it's not just easier to do, but that's also a side effect. It is just one element as we normally always wanted. So actually the 250 is quite a decent number of elements. And of course, if we think back about how difficult it was to make the segments for a uniform section, then what about if we use web tapering. If we have web tapering, then there's even additional thing that I need to calculate manually the actual height at every location. And if I change anything, then I need to do that again and again and again. So the new functionality appears in Consteel as a new add-on type to members. Like the previous tapering was also an add-on. That means that first I had to define a beam, and once I had the beam as a starting element, I could put this extra information on that beam element. Same way works the new one, as also has a symbol of an eye section inside. This function is dedicated to eye sections and of course welded eye sections. We didn't cancel the old functionality. It's still there. If somebody wants to use it, it's unchanged. It's there. That one is not only applicable for eye section, but it's also for some sort of hollow section, pipes, used channels, and others. So that has a much wider range of application, but it's not so specific to the welded section. What appears as a new one is the macro for the welded section, a new add-on possibility. And what is very important, that all this information, what you can see here, are handled by an internal table inside the macro. So that means that I just directly give as input exactly that information, what is in my mind, what makes sense to construct the element. I don't need to think about how many finite elements, how many segments, how many profiles will have to be created. That's up to Consteel. I just give this table to the member, and I can freely change it. I can add new elements inside. I can delete something inside. I just update the table, and once I click OK, Consteel will automatically update the model accordingly without me to spend time in it. And of course, we can do also web tapering, not just uniform section, uniform height, but also the height can be changing. I can give a height change along the length. At the moment, only linear tapering, so that means that the height increase can linearly change from point A to point B, but it cannot we cannot make a combination of a linear and uniform pump together. If you want that, then you need to have two members. One is linearly changing, other has a constant depth. But of course, web tapering is also a parameter which comes into the game and can be done. What I want to demonstrate for you, and it's also a small demonstration of the capabilities of Consteel alive, is that we have this frame, like a starting frame, using everywhere the new elements. You see when I click on it, I see already now this new web tapered element. This is the one I created with this function. So in order to use the function, I need first a column and beam element already placed, and then I can define it on top of it. What is very important is, and it might be a bit misleading at the beginning, is that the original, so when I first make the column or the beam as the reference, then it needs to have a profile. That's part of Consteel. In order to define a member, I need to have first a profile. That profile is basically just an internal fallback profile. It's not necessarily the profile of the final product, because I can change everything by myself. So for example, I can change the width of the flanges freely. It doesn't necessarily need to keep the one which was used for the creation of my starting beam. I can override that flange width the way I want. I can use the same value for the two flanges, or I can use different values for the flanges. I can also change the depth of the profile. So it's the actual depth of the profile. It's not controlling the final appearance of my element. That was just the start to start with, and then I can freely change even the height. And plus, of course, I can change all the components like web thickness and flange thickness separately in the table. So the reference profile is only there as a reference, but it's not something that I need to change manually to follow my actual shape. And of course, Consteel will not even change it. So that reference profile will always remain there as a reference profile, which you can later on change quite drastically with the different parameters. Okay, so now what I have now here is a normal simple frame, nothing special, it's just completely random thing. There is a uniform distributed load to represent some dead load type of thing, and there is a let's say, a snow load type of non-symmetric loading. There's no wind load, there is nothing special on it. And I just very quickly want to show, and again, as a sort of reminder of what we always recommend to use Consteel and how the different steps. So this is a portal frame. This is not only a 2D model. Of course, for a 2D model, I need to create, I need to perform the cross-section strength verifications. And once the cross-section strength verification have passed, then of course I shouldn't forget about stability verification. And here, in plane and out of plane are two different things to deal with. We use for the buckling verifications the general method. The general method is out of plane only. This is something that we always repeat, and you should not forget. The general method is an out-of-plane verification. That's why if you look to the Eurocode, it's also the slenderness used by the cushion is called lambda OP. OP means out of plane. Of course, in case of a portal frame made with I section, almost always the dominant direction is out of plane, which means out of plane flexural buckling, torsional buckling, or lateral torsional buckling, or any possible mix of the three. The in-plane buckling is typically the in-plane flexural buckling of the columns, which is probably rarely really causing big problem because they have huge inertia in the plane compared to the out of plane. So here this section, it stands with its major axis and is 600 millimeter deep, while the flange is only 100 millimeter wide. So obviously just the dimension wise is 4 times bigger. And of course the whole topology of the section is that it creates big inertia in this direction and very small in the other direction. So the two inertias are very different. And even if we have intermediate supports along the length, typically almost always the out of plane will control the design. But it doesn't mean that we are allowed not to do the in-plane. In-plane must be also done. In-plane is recommended in Consteel to be performed by defining imperfections, bow imperfection elements. What I made now here is that I used a parameter of bow imperfection, which is defined as L over xxx, where xxx is coming from the Eurocode. So you can look to the actual profile what you use in plane direction, YY, buckling around YY, and select the value according to the Eurocode and define as bow imperfection. This bow imperfection will be automatically applied to the finite element model. It will not change my geometry of my structure, but I define. It will just consider during calculation. This is the bending of the columns. And in addition, because the sway structure, I need to apply also global imperfections. In order to define global imperfection, the best way in Consteel, you have a big choice to do how you wish, how you want. That we can define notional loads. This is mainly a UK, US type of approach, that a certain percentage of all the vertical loads can be converted into a horizontal load and placed on the structure. A more Eurocode friendly option is the so-called what we call as initial sway, and this is what I did now. In the positive x direction is always shown on the icons. In the positive x direction, I apply inclination of the columns with the L height over 200. Unfortunately, this is something that we will need to fix it. There is no any visual representation of this impact on the structure, okay? So you will not see it. There is nothing. The bow imperfection is visually shown so that you can always double check is there. This is not seen. The only way to check it is that you come here in the definition and first of all you see if there is such a definition made. And the other thing that this will only be considered for the calculation if it is specifically selected here. But there is no any visual representation of the sway imperfection, okay? So let's say what is the type of calculation steps. So first of all, I need to do just a cross-section check. Let's say I start with, I don't want even imperfection, nothing, just first order analysis. If my profiles are not strong enough to carry this vertical load and this snow load type of thing, of course, it makes no sense to speak about in-plane buckling, out-of-plane buckling, lateral torsion buckling. Of course, the structure will fail. So first, I just make a calculation with first-order calculation on the structure. It's easy because we have just a small number of combinations. If we had more combinations, then we could use nicely the combination filtering option if Consteel, which I haven't used now. but it's a very efficient, and I call everybody's attention. We have some nice description of the proposed recommended way to use it in our knowledge base. It's very aggressively and very efficiently reducing the number of combinations. I see with sometimes very big sadness the models you send to us that 600, 2,000, sometimes even 10,000 combinations are in the model, and each 10,000 combinations are always calculated. It may take hours to do a run. So it's really completely unnecessary in most of the cases. If you use the automatic combination generation of Consteel, we create many combinations. Simply, this is the concept of Eurocode, but it doesn't mean that all are realistic. It makes no sense to make a lot of calculation with those many unrelevant combinations. Node combination filter is something very useful and can be very nicely used. Now, I don't need it because we have just only 6 combinations. What I can do now is go to global checks. First of the results I can do only cross-section check because I haven't done any buckling verification yet. Anyway, I just want to check the cross-section check strength, and what is already visible here is that we have slight overstresses in the structure. So in the column and also in the beginning of the rafter, the utilization ratio for the cross-section strength versus demand, bending moment normal force, is already not full satisfying the requirements, and the section must be strengthened. So the most visible differences are on the column, and the rafter is less critical. So let's say that I want to a bit more drastically help to the columns. Sorry, my computer is a bit slow. I just got some, again, some Windows updates. So what I can do now is I change the flanges of my 2 columns from the 150 to 180. Now both have changed to a wider position. I can also check by coming here, and now it's visible that the column is somewhat wider than the flange. Everything is always in scale in Consteel. You can always see it. So I change now to 180. And what I can do now is that I run again on the calculation. Of course, this is maybe not something that we would expect too big changes from, but at least let's see what is the impact. Now, we still have a very small location here in the rafter. We will solve it differently, but at least in the column, it was well enough, this increase for the inertia. So it's fine. Let's go to buckling verification, because obviously that might be still critical. When we are at 100% or even above 100%, when we add buckling, out of plane buckling verification, then obviously we will have issues. So when I activate buckling analysis, Consteel will calculate the linear buckling eigenmodes of the structure. And once I have the linear buckling eigenmodes of the structure, I can use them using the buckling verification with the general method for the out-of-plane direction. Out-of-plane direction means out-of-plane flexural buckling, torsional buckling, lateral torsional buckling. These are all covered by this verification. I haven't run buckling sensitive analysis first. I can just use the very first buckling mode shape at the moment of structure, but it already gives a first idea of how big chances the structures are to survive. Not too big. The stress-wise, it was more or less okay, but visibly there are huge problems with buckling problems. If we look to the linear buckling results, which were used for the buckling verification only in the first mode, visibly the bottom flange of the rafter and also of the column are moving outside. This is a pure lateral torsional buckling type of thing, and of course I did nothing to prevent it. I just stabilized at the moment the structure on the top flange, and then nothing to prevent it. What is very convenient in case of metal building practice is to use some so-called of flange braces. At the moment, for simplicity, I define infinitely rigid out-of-plane supports, although this is probably not the reality. We had several trainings. We will also repeat it later on when I will speak about that. It's very important not automatically make the simplified modeling. Simplified modeling might be unsafe. Normally, in a wrist structure, that bracing provided by just an angle connected to a cold form purlin, it will never be as efficient as a considered fully efficient, fully rigid lateral support. It will be something with a certain flexibility, and that is much closer to a spring value with a questionable unknown value, then a rigid support. Okay, so when I said rigid support, then of course I'm probably doing some sort of simplification, which maybe is not too much valid, but now for the show the sequence of working with Consteel, this is perfectly fine. I will also add one maybe to the column. And now I repeat the calculation now. And now, because I believe I would want to do something more precise, also I want to activate buckling sensitivity analysis. Buckling sensitivity analysis is that part of the feature of Consteel I don't want to speak now about, but this assigns the appropriate buckling mode shapes to the different members of the structure. Without that, just using always the first buckling mode shape, the design is very conservative. Now by adding the buckling mode shapes also in the result, in the calculation, I can now activate the buckling mode check with the arithmetic option, and I do the calculation again. And if I'm lucky, then I will see already more or less working situation. The rafter is more or less fine. We still have some issues here. The column is still very red. Let's say that I want to solve now the problem of the column by playing with the thickness of the flange, because my original structure as defined was built with 10 millimeter of web for the full length. Let's say I want to have here a thicker web for the top, and just this 10 millimeter keep only for the first part. So I click the add to add the new segment, and it's my choice whether I want to start the definition from point A or point B. Now at the moment I start from point A, which is at the bottom. So I need to add the 10 millimeter thickness. Let's say I accept this 3,000 meters. So from here up to there, it will be 3 meter long, will be 10 meter thickness. But for the rest, I want to change it, let's say, to 16 millimeter. And when I click OK, then you see immediately two things. A break line appeared in the section. So that means that internally, Consteel has already splitted the member into two, but it's still one member, so I don't get two members. And if you zoom in, then you will see that now here the thickness of the flange is really much thicker. I need to do the same also on the other. I could have done also in one step for the two, but I haven't done. So now I just, again to show, I click the plus, I accept this one, and I change the other thickness to 16. And when I say OK, it's fine. And then maybe also, yeah, it's maybe it will be enough. Let's see what happens. And there is still important, I haven't, all the analysis is first order, and I haven't done anything for in-plane yet. Okay, so that's still important to remember that still needs to be done. So now I run the calculation, still first order only, buckling calculations, and when I run it, I will see that now my column is more or less fine. There is still a part here where the section is not appropriate. Let's say I change now the depth of the profile from 600 to 700. That will also showcase for you how nicely all the information is kept. So now the geometry is changing. The sections will be bigger to the inside, as I said, because I used for the eccentric position this sort of relative system. All the section changes can happen only to the other side. So the other side of the column became deeper, and I don't need to move the columns more to inside the rafter to below rafter, because the geometry is kept as desired, and I can do all the changes. All the position of the supports, everything is automatically moving because they are all placed with the smart link. The smart link is keeping the instructions for the rule and not the actual position. And when I run it now, hopefully it will be much closer to a working structure. Everything is below 100, but I haven't done in plane yet. Actually, I defined imperfections, but I haven't really applied on the structure. In order to apply the in plane imperfections in the structure and consider them in a GNIA second-order geometric and nonlinear calculation, of course, I need to activate second-order analysis, plus I need to activate the sway imperfection, which will move with an angle of 1/200 in my structure. Only this will make the design complete. So if you don't do this and you don't make second-order analysis, then your design is probably not complete. Whether first-order or second-order analysis is accepted, it's regulated in a more general sense by the Eurocode. But if you want to use imperfections with this methodology that I show, then regardless of that rules of Eurocode, whether first or second order would be enough, you always have to use second order analysis, because this sort of imperfections will be applied through the second order analysis only. So when I run the calculation with the second order analysis and in-plane imperfection, I cannot change the internal forces to second order, and I don't change anything here. And I just do hope that there will be no drastic changes. As you see, 99.1 went up to 99.6. So usually in-plane buckling is not relevant, but it doesn't mean that you are allowed not to do that. With this new welded function, it becomes very easy to play, to adjust the different components, making the columns and beam elements, add change, remove change the thickness along the length. With the new offsetting option, you can very nicely fix those positions of the structure which you don't want to change during optimization, and making very clear that on which direction your structure's elements will be deeper or narrower as a consequence of your changes. You will not need to modify your geometry, and the calculation model is always perfectly available according to your data. So this is just, I really wanted to show as a flow of working with Consteel, and basically that is also the end of my calculation presentation. I just quickly see some questions which appeared here. Does the analysis allow for load eccentricities due to beam offsetting? Load eccentricity due to beam, sorry, I don't really understand. Load eccentricity always existed in Consteel. So with that, we didn't have to do any new developments. The only thing we did as new is that we added, just for generality, also the new positions for the load, although probably it's very rare that somebody wants to apply a load at the web and flange intersection point, but why not? But I'm not sure that you refer to this one. Next one, it should be possible to apply different sway directions to use different combinations. Yes, you are fully right to use different sway directions for different load combinations. At the moment, for one combination, you can set one value. This is how Consteel is set. And I think it's most usually also the situation with any other software that you need to define an imperfection for the calculation. And of course, if you have all the other effects in the other direction, then this is not so relevant. There are some tricks to overcome it. One is that if you use equivalent loads can be automatically placed in the worst direction. And what we are also working on now, I don't know when we will have a visible result in Consteel, but if any of you wants to come to the Eurostay conference in Krakow this year, then you can see our presentation. We are trying to provide, to extend this limitation of the general method, not only for out of plane, but to have the same type of methodology, same type of freedom of working also for the in plane, although, as I said, in most of the cases, it's not so relevant, its importance, but it's very important for the correctness to be covered. And what we want to do is that we release this need to specify by the user an appropriate imperfection for the structure, but we want to use automatically the imperfection selection and consideration in the calculation. That would also mean that with that feature implemented, there will be any problem with the positive or negative type of, or any sort of other sway. Consteel will always select the appropriate sway imperfection from the available elastic buckling mode shapes, and we'll always scale them accordingly to the worst direction. So that would be something hopefully coming soon, and that will simplify the work. Up to now, what you need to do is really make sure that you apply always to the good direction. I'm not saying that you are ready to cheat, but also in this example, I've shown that usually it has a very small importance. What is very important for sway is the alpha critical of the same sway mode. If the alpha critical of the sway mode is less than 10, then it's very important to deal with, and then you cannot cheat. If it's the alpha critical is around 2 and 3, then it becomes extremely important. You will never get that in frames with 2 columns only. You can have very low alpha critical only if you have very wide frames and you have a lot of columns, intermediate columns with some pipes, with pin-pin connection, which don't contribute to the sway stiffness. Then you can have extremely low alpha critical value for the sway mode, and that is already very critical. But as long as you have portal frames of this kind, and if you look the in-plane alpha critical, it very often is around 20, 30, 40, or something very big value. Actually, it doesn't produce anything. So if during the optimization, you don't really need to take too much care. If you are ready and you want to have a correct documentation and you want to prove that you checked everything, then it's well enough to create then the categories of the load combinations and select the left from right type of combinations and separate from the right from left. And yes, at the moment, you will need to have 2 different imperfections. In worst case, 2 different models, one saved with the positive values of imperfection, other saved with the negative values of imperfections. Okay. We have to check only inclination x plus. What about x minus? This is a symmetrical structure, but of course, if you speak about sway, then yes, of course, we should have checked that as well. At the moment, I made a structure where also the asymmetric snow load is also moving the structure from left to right. So therefore, the positive x direction is the appropriate one for the corresponding sway. But of course, in a much more general structure, I don't know in advance, especially if it's a monosymmetric structure, then I really don't know which direction of imperfection will be, sway imperfection will be controlling. Both must be checked. As I said, at the moment, there's no any automatization for that. The only good thing is that you keep in mind, as long as the alpha critical of the sway mode is high enough, above 10, then it has very little impact. So therefore, you don't need to care too much about that. You can optimize the structure without, and just when you feel that you are ready, then you want to make sure that really everything was checked, then you can do that. But at the moment, this is really might require different calculations, because you can always just set one sort of imperfection. I mean, left or right. Okay, so thank you very much for your interest. We were longer than planned, like always. I hope I didn't take too much of your time. I hope you have maybe seen something interesting here. If you have any question related to these or anything else, you can find us on our support, and we are happy to answer any possible questions you may have. And if somebody feels that this Consteel light, it might be an interesting option for them who are not Consteel users yet, but they would want to start to explore the possibility of Consteel and start with smaller project to complement the other software they might use for structural design. Consteel Light is a software dedicated for these demands. So I warmly invite anybody to download the trial version of Consteel for free for a month, and then you can see it and you can check it, and hopefully we can welcome more and more customers who are ready to come into this challenging work to explore stability verifications and really understand how structure behaves realistically. That's very important. That's why it's our slogan. We want to calculate truly the structures. Consteel can do that, and that's very important. Thank you very much for your interest, and have a nice afternoon. Bye-bye.